I have introduced differentiation by saying it is the process by which we can take an original function and turn it into a new function which will tell us the rate of change, or the gradient, of the original function at any point we like. Every function has its own associated differentiated function, which can be derived from first principles. This is, however, very difficult in most cases, and so instead of having to derive everything yourselves, you are given a list of types of functions which we know how to differentiate easily, and you can work out how to differentiate most other functions using this list. It is useful to note now that if we have a function that is a sum of multiple terms, we can differentiate each term separately. So differentiating, say, f plus g is the same as differentiating f and g separately and then adding the results together. The first type of function we look at is the polynomial. A polynomial is a sum of terms with different powers on the argument, which is usually x. This is an example of a polynomial, and you can see that the general form of each term is a constant followed by x to some power. Since when we differentiate, we deal with each term separately, we can just look at the form of one of the polynomial terms, which we write generally as a multiplied by x to the power of b, with a and b just being constants that can take any value. We know f of x is of this form, and now we want to know what the differentiated version, f primed of x, will look like, which is the result of differentiating f of x. What we do in the case of polynomials is we take the power b and we bring it down and multiply it by whatever constant is in front, a, and then we decrease the power on the x by 1. This leaves us with the general form ab multiplied by x to the power of b minus 1. For example, if f of x is 3x to the power of 5, then f primed of x is 15x to the power of 4. The next types of functions we look at are the trigonometric functions sine x and cos x. The differentials of these are easy to remember. We find that when we differentiate sine x, the new function we get is actually cos x, and when we differentiate cos x, the function we get is negative sine x. The exponential function e to the power of x has the remarkable property that when we differentiate it, it stays the same. F primed of x is also e to the power of x. This means that at every point on the exponential curve, its y-coordinate is the same as its gradient, which is also the same as the rate of change of the gradient, and so on. The logarithmic function, ln x, differentiates to the function 1 over x. To emphasize, if we wanted to know the rate of change, or the gradient, of any of these functions on the left-hand side at any given point, we just insert that point into the function on the right-hand side. For example, the gradient of the sine x curve at x equals 0 is equal to cos of 0, which is 1. The gradient of ln x at x equals 2 is equal to 1 over 2. From these building blocks, we can differentiate a lot of different functions. We must remember two things. One is that we differentiate each separate term in a function independently. And two is that any coefficients or minus signs in the original function must still be included when we differentiate. For example, if we differentiated f of x is equal to 2x cubed plus sine x plus 2 cos x minus e to the power of x minus ln x, we would get 6x squared plus cos x minus 2 sine x minus e to the power of x minus 1 over x. You can see that the 2 in front of the cos x stays when we turn the cos x into a minus sine x, and that the two negative terms at the end will stay negative.